Assalamu alaikum dear students, I am engineer Abdul Basit and we are in lecture number 26 of week 13 and the topic for today's tutorial is few numericals on hydraulic conductivity procedures. So here we will solve numericals on both the procedures on the constant head permeability test procedure and on the falling head permeability test procedure. So already we have discussed these two methods in the previous lecture number 25. Okay, and these numerical will be based on the laboratory procedure and as well as on the practical and field procedure. Okay, so we may have some situations in the field which can be in contrast with the situation in the lab available. Okay, so how to tackle these situations, that will also be discussed here. So in this tutorial I have taken an example from the Baraja Imdas book. So the statement is refers to the constant head permeability test arrangement, gives the following value. So this is that arrangement. Already we have discussed this arrangement and this diagram and in the previous lecture, which was about the constant head permeability. So this is that arrangement for constant head permeability test. Okay, simple. All the values given here are length of the sample, that is 30 centimeter. So this is the length between this perforated or porous stone, which is sandstone, from here to here. So in between these two stones there is a soil sample placed and which is having a length of L. Okay, so the length given here in this practical example is 30 centimeter. Okay, now area of the specimen, that is 177 centimeters square. So area of the specimen refers to that this is like a cylinder, okay, in which the sample is placed. So if this is a circular cylinder, so the area of this circular cylinder. Okay, here it is only a cross section given. Okay, so this may be a rectangular or a circular cylinder. Most probably this is a circular cylinder. Okay, so the area will also be in circular form. Pi d square divided by 4 will be the formula to use it, okay, in case the diameter is given. Okay, so here directly the area is given, no need to use any formula over here. Constant head difference, that is h, which is given 50 centimeters. So head difference, this is head difference between these 2 points, that inlet and that outlet point, which is h. Okay, so 50 centimeter is given over here. Water collected in a period of 5 minutes. So the total time for which we have operated or we have performed this experiment is 5 minutes. Okay, so this is t, and 350 centimeter cube is that volume of the water that is collected. So this is capital Q. Okay, this is that volume of the water that is connected over here in this graduated cylinder after passing through this sample. Okay, so now calculate the hydraulic conductivity in centimeter per second. So this is the unit we need to determine. And simple, you need to find out that coefficient of permeability. Okay, so this is that equation we have already discussed in a previous lecture. So here it is QLAHT. Okay, Q is that volume collected in the you can say in the graduated cylinder. So here it is that volume collected over here, that is 350 centimeter cube. So straight away you have to put it over here. Then length is 30 is given here, this is 30. Okay, 30 will be put it over here. No need to convert the units already given in centimeters. All the units are centimeter, and here it is in minutes, it will be converted. Okay, 177 again centimeter square, so no need to convert it. And 50 is again this is the head, which is in centimeters, no need to convert this. And 5 is in minutes. Okay, so we need to calculate the hydraulic conductivity in centimeter per second, not per minute. Okay, so this minute will be converted to seconds first. So 5 multiplied by 60 is just to convert it in seconds. Okay, so after calculation you will get this value, which is in centimeter per second. So this is quite simple numerical, okay, on the laboratory condition. Similarly, if we are going to discuss the same situation for falling head permeability test, so what will be that procedure? Simple, this is that arrangement given, okay, for falling head permeability test. Already I have explained it in previous lecture. This is that cork at the top and bottom, to hold the assembly of the inlet pipe and the outlet pipe. And here it is that soil sample, okay, between two sandstones, okay, or porous stones, and the head difference between the inlet and outlet, that is H given over here at any instant whenever you want to, and this H1 and H2 is are any random heads at any random times, T1 and T2. Okay, so this is a standpipe. So all the assemblies already are explained in the previous tutorial. Now the values given over here are length of the specimen, that is 20 millimeters. So this is in millimeter, the length of the specimen from here to here. Okay, area of the soil specimen, that is 1000 millimeters square. So area of the soil specimen, again as we've discussed in the previous numerical and previous lecture too. Area of the standpipe, so this small a will be equal to 40 millimeters square according to this numerical example 7.2. okay, head or difference at time t0 is 500 millimeter. So time 1 is 0 and the h1 is 500 millimeter, and head difference at time 180 seconds. Okay, so 180 seconds mean 3 minutes. After 3 minutes, so the head was 300 millimeters. So this is h2. Okay, this is h1, and at this point the time was 0, and at the next point it was 180 seconds. Okay, you need to determine the hydraulic conductivity of the soil in centimeter per second. Okay, so how to do it? Simple, use that equation we have already derived in the previous tutorial. K is equal to 2.303 ALAT log 10 to the base 10 and h1 divided by h2. Okay, so all the values are almost given over here. 2.303 is constant. A is given over here, that is 40 millimeter area of the standpipe, this thing. Okay, so this is given over here. L is also the length of the specimen, which is 200 millimeter, and A is the area of the soil specimen, that is 1000 millimeters square, and T is the time, initial time, or the for which it was performed, the total time for which the test was performed. So it is 180. Okay, and h1 and h2, so this is h1 500, h2 is 300. Okay, so this is that all the situation given over here. You just need to do the calculations and it will be the answer given in centimeter per seconds. Okay, so this is hydraulic conductivity according to the falling head permeability test. So in these two numericals, the basic thing is just to keep in mind which formula needs to be used. So first of all, get it confirmed from here. If it is falling head permeability test, so this formula should be used. If it is constant head permeability test, here it is given constant head permeability test, so you must be sure about this formula should be used, and the perfect formula for constant head permeability test. Now coming to some practical situation, practical field situation. Okay, so let's say we have a permeable soil layer is underlined by an impervious soil as shown in figure. Okay, with K is given 5.3 multiplied by 10 raised to power minus 5 meter per second. So this is that coefficient of permeability already given. Okay, for the permeable layer, calculate the rate of seepage through it. So we need to determine the rate of seepage through it, how much of the water is passing through it, and this is that rate of seepage formula already we have discussed in the previous tutorial, and we will explain it right now as well. So that is like Q into is equal to KIA. So this is that formula we have discussed in the previous tutorial. Okay, that will give us the seepage rate through the soil sample in meter cube per hour per minute. Okay, per meter, sorry. Width if h is 3 meter and alpha is 8 degree. So the situation here is, let's say there is a soil sample which is placed on a hard strata. Naturally, okay, or you can say underlined by a hard strata impervious layer. So this blue red this dark blue color actually shows the impervious layer, and this one shows the pervious layer of the soil, permeable layer of the soil. Okay, and on the permeable layer there is a layer of water as well. Okay, so up till this is the layer of water, and the seepage direction will be in this direction. These arrows shows the direction of the seepage or the direction of flow of water. Okay, this is that groundwater table. So above this permeable layer there is also some soil placed, not simply just water. Okay, but we are concentrated on this soil that is in the form of an inclined layer. Okay, this is also an inclined layer. So how much inclination is there with respect to the horizontal? Alpha is given. Okay, alpha is 8 degrees. So with respect to horizontal, this is that horizontal, the angle is given, that is alpha. Okay, the head of the water at this point is given, that is h. Okay, and at this point this need to be determined. Okay, so for the calculation of that formula of for the calculation of that rate of the seepage, we need to just do this thing. Okay, for that I am just minimizing it to make this formula visible to you people. That is QIA. Okay, Q is equal to KIA. So Q is that volume of the seepage water through the soil sample, and K is coefficient of permeability, I is the hydraulic gradient, and A is the area. So this is the formula. For this formula we need to find out the K first. Okay, so already K is given here in this table, in this statement. This is 5.3 multiplied by 10 to the power minus 5. Okay, and I needs to be determined. I is the hydraulic gradient, and A needs to be determined. So already we know that I is equal to head loss. Okay, this is that the head loss divided by length. Okay, head loss divided by length. So how to determine the head loss and length, it will be cleared right now after some time. And A is the area of the cross section of the soil sample. Okay, so here it is. Let me make it clear first again. Okay, here it is. This situation is drawn over here in the simple form. So and just in the line diagrams. So you can see that alpha is equal to 8 degrees. Okay, already it is given in the statement. Okay, this is that this line actually shows the line of the hard strata, or the transition line between hard strata and the pervious strata or permeable layer. Okay, this is permeable layer, this is the hard strata. This line is actually drawn over here. Okay, sorry, here. Okay, and this is that line, or the line drawn for the water table. Okay, this line shows the water table. Okay, and similarly H is given, which is completely in the vertical direction. Okay, and it's not perpendicular to this line of the groundwater table. Okay, this is not perpendicular to it. This is completely vertical line, H, the head at this point. Okay, now coming to this situation, simple. H is given over here in this form. This red line shows the H. Okay, and this is that complete cross section of the soil sample, which is perpendicular to the flow of water. So this is that cross section we need to determine. Okay, and for this cross section the area needs to be determined. As in the previous laboratory test, we are going to determine the area that is perpendicular to the flow of water. Okay, so simple. This black line actually shows that that perpendicular area which is perpendicular to the flow of water. Okay, and by drawing this line, this will be a complete triangle now. Okay, so already this red line is H. Okay, and here at this point this will be the alpha between this red and black line. This will be the angle. Okay, by using the transitive property. So here it is the alpha, the angle at this point and at this point will be equal. Okay, so simple, you can say that this is the triangle in which this black line is the base, and this red line is actually the hypotenuse. So cos alpha will be equal to base by hypotenuse. Okay, so base will be equal to this black line, which is equal to h multiplied by cos alpha. Okay, and h is equal to 3 given over here. Okay, this is h and this is given over here, that is 3. Alpha is 8. Okay, so now after drawing this triangle, this will be the for area, or you can say this will be the length of this black line, okay, which is completely perpendicular to the flow of water. Okay, now coming to the next thing, this is S. Okay, and here this line is completely horizontal line, okay, which is drawn at an angle alpha to the this line of the groundwater table. Okay, and this horizontal line actually shows S. Here it is S, here it is S. This is between these 2 points, and similarly these 2 points. This is S. Okay, not completely till this point, just till this point. This is S. Okay, we need to find out this line. Okay, so how to find it out? Just this is the value for this line. How to do it? This is alpha, this is alpha. Okay, or you can say in this triangle, okay, how to do it? This is alpha. If this is alpha, this will also be alpha. This is also alpha, for which base is S and hypotenuse will be equal to, simple, we can calculate it by cos alpha is equal to base by hypotenuse. So base will be so hypotenuse will be equal to S divided by cos alpha. Okay, so this is simple geometry. You can do it on your own as well, but just you need to determine the position of the perpendiculars and base, and also the position of the alpha where it would be. Okay, so if that is clear to you, then simple geometry you can determine any side of the triangle from the simple geometrical equations. Okay, now if this is S divided by cos alpha, so this line is also equal to S divided by cos alpha. We need to find it out, this thing. Okay, because at this point the head is equal to h. At this point the head is being reduced to this point. Okay, so this reduction is equal to delta h. How to do it? This is actually this line which is perpendicular to this one. Okay, so the perpendicular is this is base and this is hypotenuse. This is actually alpha. Okay, alpha. So if this is base, this is perpendicular. How to do it? Tangent alpha will solve the problem, and tangent alpha will be equal to delta h divided by S is equal to tangent alpha. How to find out delta h? This is delta h. How to find it out? Delta h will be equal to S multiplied by tangent alpha. Okay, simple geometrical equation. So then if this is delta h is already determined. For I, you need to find out the head loss and the length. So head loss is given, that is S tangent alpha. This is head loss, delta h. Length is given from here to here. This is the length of the sample, which is S divided by cos alpha. Okay, so after calculation you will get that tangent divided by sine, and this will be cancelled with this one, and this will be sine theta. Okay, tangent multiplied by cos alpha is actually equal to sine alpha. Okay, so putting these values in, Q is equal to KIA. K is already given in the statement, that is 5.3, and I is equal to sine alpha. So here it is sine alpha, and A is actually equal to this cross sectional length multiplied by the width. So width can be considered as this is that practical example, practical soil, so it can have infinite width. Okay, but for this numerical we are going to take the unit width, which is 1 meter. Okay, so unit width out of the plane. Okay, out of the plane. This is 1 multiplied by 3 into cos alpha. Okay, so this will be that area, and this is that I, and this is K. Okay, putting all these values, for alpha you can put the 8. Okay, 8, so alpha is equal to 8, already given in the statement, and all these rest of values are clear to you. So here it is. Okay, now this 3600, how to do it and why to do it, this is already these values will be given in seconds, as this k is given in seconds. Okay, and we need to find it out in hours. So how to do it? Just for to convert it from seconds to minutes, multiplied it with 60, and from minutes to hours, multiplied it with 60. So 60 multiplied by 60, this will be 3600. Okay, so this is that volume of the water or the seepage passing through happening to this soil sample. Okay, and that is equal to 0.0789 meter cube per hour per meter. Okay, so again we have another practical example. This is actually the continuation of, or you can say a bit similar to this previous numerical. Okay, here it is, the statement is given in the 7.5 numerical. This is again the example taken from Baraja Ahmed's book. Find the flow rate in meter cube per second per minute. So here it is a bit change from the previous numerical, where the unit required is meter cube per second per minute. Okay, in the previous numerical it was meter cube per hour per minute per meter. Okay, at right angle to the cross section shows through the permeable soil layer shown in the figure 7.10. So this is, here it is given, h is 8 and h1 is 3. Okay, and h is equal to 4 and s is equal to 50, and all these values are given. K is also given, alpha is also given. So again you will do the same geometrical calculation for this as well. This is the base. Okay, alpha is given 8. Okay, if you want to find out this hypotenuse, so how we will do it? Simple, this will be that hypotenuse. Here it is, from where can I do it? This thing, s divided by cos alpha. Okay, s divided by cos alpha, and the head difference between these 2 points is already given. This is 4. So hydraulic gradient will be equal to h divided by this length, which is equal to s divided by cos alpha, as we have done it in the previous numerical, s divided by cos alpha. This is same situation, and we need to find out the area. Okay, so area, so for area this is h, which is completely vertical, and for this inclined portion which is perpendicular to that that transition layer between these two layers, so this will be like h1 cos alpha. Okay, multiplying it with 1 will give us the area. Okay, why we are preferring here the value of 1? Because the width can be unlimited and we are taking it just unit width. Okay, so this is completely similar to that previous numerical. Putting value of k, I is also given. So after this calculation, h cos alpha divided by s, this will be that I, and also h1 cos alpha, this is the value for area. By putting all these values, you will get the answer, which is 0.19 multiplied by 10 to the power minus 3 meter cube per second. So all the values are in given in meter cube per second per minute. Okay, so that's all from these numericals. Okay, and I hope you have got something new to learn. And in the next tutorial, inshallah, we will discuss about the seepage through the soil sample and the Laplace equation. So here are some visual of these phenomena. Okay, we will discuss it later in detail, inshallah, in the coming tutorial. Thank you very much for watching. Assalamu alaikum.